Okay, so stochastic modeling. What I want to do now is to introduce stochastic modeling by making reference to probability theory. And in order to do so, I need and I would like to remind you some basic concepts of probability, because I think it's important to recall some basic concepts in order to better introduce stochastic modeling. And also I think that the way in which I may present concepts could be clearer from an engineeristic point of view. So I would like basically to go back to some basic probability theory, not spending much time. And what I would like to anticipate is what's the difference between stochastic modeling and the usual examples of probability theory that you well know, like tossing a coin. Tossing a coin is a classical probability experiment. I want to make clear what's the difference between stochastic modeling and a basic probability experiments like tossing a coin. And I would like to do so because very often stochastic modeling is considered a complicated and nasty topic, while actually it refers to experiments and results that are very much intuitive and can very much explained with personal experience, expert knowledge. And what I would like to do is to continuously keep a parallel between the theory, in this case of stochastic modeling, and what our understanding would suggest. This is possible, and this is my aim. This is what I would like to try. So let me make this parallel. Probability theory refers to experiment, as I said. Stochastic modeling is the same. So let's see what's the difference between the two experiments that we want to describe. Probability theory basically refers to events that are outcomes from experiments that are well defined, experiments that we can easily understand as single outcomes, like tossing a coin. I toss a coin, and the result is the outcome from a single experiment. If I make another toss, then it's a second experiment, and the result is just one. Another example could be annual maximum flow for the Po River. You pick up during 1 year the maximum, and this is an experiment. It's a number. 1 year later you pick up a second number. This is the experiment. Another issue could be, another significant example could be annual maximum rainfall for a given location. Okay? There is one basic concept that often is not mentioned, very important assumption that we make about this experiment. They are independent, very often. We can remove this assumption, but basically, when we speak about tossing a coin, we implicitly assume that the two results of two different experiments are independent. Which means that, of course, if you toss a coin, the result that you get is not influencing your next experiment. And the current experiment is not influenced by the previous one. If yesterday you toss a coin and you got a net, today you cannot say anything about the new results of the experiment. It's not influenced by yesterday. While you can understand that if I make another experiment, which is going to the Po River every day to measure the discharge, the results of this experiment, the results are not independent. If today I measure a very high discharge along the Po River, tomorrow I will expect to measure an high discharge as well. Because the two experiments, the two results are not independent. Dependency is a complication. If you want to analyze the results of tossing a coin and you allow some dependence, the result, the analysis of the experiment is more complicated. Of course, because you know, you can understand that the Po River every day is more difficult to understand the mechanisms. It's more difficult to understand with respect to tossing a coin. So the result is that when there is dependence, the experiment does not consist in a single outcome, but instead of a series. So let me better explain. If you talk about measuring the discharge of the Po River, the result every day, because timing is essential every day, the result of the experiment is not a single measurement. The result is a series of measurements. You are forced to consider a series of experiments, of results, of measurements, in order to take dependency into account. Dependence into account. So the difference is that when there is independence, you can focus on a single experiment, a single measurement, a single outcome. When there is dependence, you have to focus on a series. So let's go to our problem. If you measure the annual maxima, you can assume very easily that the maximum in every year is independent of the past and doesn't affect the future. If you take the maximum river discharge of the Po River in 2011, you are not expecting that it's influencing the maximum discharge that we will experience in 2012. This is quite intuitive, quite obvious. As long as, in the same ways as you recognize dependency in daily flows, you understand that dependency in the annual maxima is not there. So if you talk about measuring the annual maxima, you can define it, you can describe this experience, this measurement with the probability theory. If you instead want to analyze the discharge in every day, probability theory needs to be adapted to take dependency into account, and you can't consider any single outcome but a series. Now, the parallel in probability theory from the single experiment in absence of dependence. If you want to move to the situation in which you have dependence, you can't use just probability theory. You need to use stochastic modeling, which is a branch of probability theory that models series of data, not just a single outcome. So this is the reason why I said I have to use stochastic modeling if I want to generate synthetic series of river flows, because I have to generate a series. It's not a single outcome that is important for me. If I want to generate a single number, like the annual maxima, then I can use probability theory, and the experiment is just made up by a single outcome. If I want to measure a series of data, I have to model the whole series. So the result of the experiment, again, is not a single number, it's a series. So if I want to generate 10,000 years of data, of daily data for the Po River, I have to generate a series. The series is the outcome of the experiment. And it's called this outcome realization of the process. Stochastic modeling is also is used to deal with stochastic processes. The model is a representation of the process, so stochastic modeling refers to stochastic processes. And we see that the outcome of this stochastic process is a realization, it's a series. We call it a realization. So this is important to understand the difference. In one case, I just have one number. If I want to estimate the design flood, the experiment consists of just one outcome, the annual maximum. If I want to estimate water resources availability, my outcome is a series. And therefore, I need to use a different tool, which is stochastic modeling. So you now expect that the result is a series. So it's not like tossing a coin where you get head or cross. In this case, you get a packet of data where dependence is reproductive. So you already understand that, first of all, you have to reproduce two important features. First of all, there is dependence. When you get your data, synthetic, the memory of the data must be well reproduced. So one needs to analyze the memory of observed data and to reproduce it. And the second issue is, of course, the characteristics of the extreme, including droughts and floods. They should occur with the same frequency as the observed data have. So if I have 100 years of data in the Po River and I observed two big floods, in actually more than two, I could say at least three, 1951, 1994, and 2000, and I generate another series of 100 years, I would expect that these extremes are reached with a similar frequency, like from 2 to 4 times in 100 years. So there is indeed the frequency behavior to be well reproductive, but also the memory. Okay, so this is the difference, this is the complication. But it's a theoretical complication because you will see that in practice the models are very, very simple, not like Grafana modeling. They are much simpler. Okay, so you see here that there is an introduction. Stochastic random processes can be used for directly generating river flow data. This is the advantage of using this method. You don't need rainfall. You just need some observed data, river flow, to understand the memory feature, to understand the frequency of occurrence, and then you can generate synthetic series directly. Second, realization of a stochastic process, a time series that is a random outcome from the process. Okay, this is what I just mentioned. The series is our results of the experiment. It's random. And I can repeat this experiment many times. I can generate as long as I want. Statistics of the synthetic series are similar to those of the observed time series. I just mentioned this issue. Frequency and memory. These are the two important features that need to be reproductive. And the last remark is just a philosophical consideration, because nature actually is not stochastic. Nature is just one experiment which is not repeatable, because in nature you define an experiment like I pick up the annual maxima, but actually the trajectory of natural processes is just one. It's our assumption to consider that we can repeat it. But this is just philosophy, don't formalize too much. I think once in a while I would like to make some philosophical consideration, because science is continuously based on making some assumption choices, and assumptions are to be made by elaborating our idea about how nature works, and this is philosophy. So I want really to stress this, because it's a way to better understand what we do, but I don't want to exaggerate. We are engineers. Okay, so now, let me, as I said, record you some basics of probability theory, because we need to set up the basis for probability, and then we extend it to stochastic modeling very easily. Okay, so statistics, this is a definition. Science, it's just, as I said, a way to analyze irregularities in the data, to understand what's going on. Okay, and this is what is important there. And probability, in particular, is a way of expressing knowledge or belief that an event will occur or has occurred. Probability theory is used in statistics. So statistics is the science of investigating data, interpreting data. And in particular, probability is a way of expressing our belief that an event may occur or not. Okay, so it's nothing else. We express a belief, like, would it be possible that Let me make a very simple example. That we can get a flow in the river of at the closure section of 20,000 cubic meters per second, and you say no, yes or no. But you say more with probability. You express your degree of belief. So it's a very useful tool, because to design or even engineering work, you just need this information, your belief about the possible stresses to which the work is subjected. Okay, and the word probability is not easy to define. You can find a lot of definitions, because you know how to express this belief. How can I say, by looking at data, of course, but even without looking at data, how can I say, how can I express my belief about the fact that an event may occur or not? So let's see some definitions. And this is very important. Let's try to understand what is presented here. There are two definitions of probability. And there is one definition that is very empirical, and it's called the frequentist definition, which means that if I want to express my belief about an event occurring or not, I just look at data and compute the frequency with which that event occurred in the past. Like Pearson did with the tossing of the coin. He just tossed the coin 24,000 times, and at the end he was able to say the probability of getting an end is about 50%. It means that he analyzed the frequency with which the event occurred. Okay? This is very simple. You make an experiment many times. The experiment must be repeatable, otherwise you can't make this understanding. You repeat the experiment many times, and then you understand how much is likely. For instance, take a series of the river, 100 years, you see 3 floods over 12,000 cubic meters per second, and then you say, I think that this kind of event may occur on average 3 times over 100 years. What you did is to analyze the frequency with which the event occurred in the past. But there are some cases in which you can't do that, because the experiment is not repeatable. Like, think for instance about some people want to build on the river some barrages to store water along the course of the river, like it's done along the Danube, along the major rivers of the world. Some people are now thinking about this possibility. Now, how would the probability of getting a flood at the closure section change? You cannot make this experiment. The barrages are not there. You have to express a belief based on something different than analyzing the frequency. The something different may be your expert knowledge, or maybe that you build a model and you try to understand how flood frequency changes. Or let's make an example that is probably more significant. What is the probability that Monti will be the next Prime Minister after 2013? You can't make this experiment many times. You just have to express your belief. Or what was the probability for Berlusconi not to finish the 5 years of the government? You have to express your belief. You can't make this experiment many times. And therefore, another definition should come into play, which is the Bayesian definition. And Bayesians assign probability to any statement whatsoever, even to a statement like Monti will be the next Prime Minister with a probability of 80%. This is not based on a frequentist analysis, just on your belief. Okay? So there are two definitions of probability. And in some cases, we can use one or the other. Now, let's focus on the frequentist definition, which is the one that is probably more tractable in mathematical terms. And let's try to define that probability in some way. because so far we didn't tell what is probability. I just said it's your degree of belief. So you can analyze the frequency or you can express your reasoning. But I didn't say what's probability. Now we have to fix some paletti, I would say in Italian, some conditions that must be met by your expressing the degree of belief or your measurement. And these are the basic axioms of probability of Kolmogorov. Any measure that satisfies these axioms can be used as probability. So let's see. Probability lies in the range 0, 1. You can express it in percentage terms, like I did before, 80%. It means, anyway, in the range 0, 1. Second, probability of a certain event is 1. Probability of an impossible event is 0. Third, the additive property, the probability of the event A or the event B or the event C is given by the probability of A plus the probability of B plus the probability of C, etc. So if your event is given by a river flow greater than 10,000 cubic meters per second, this is equal to the probability of river flow between 0 and 1,000 plus probability of river flow between 1,000 and 2,000 and so on. It's the additive property. Okay, there is an engineeristic interpretation which is proposed by Wikipedia, at least it was last year. Probability expresses the likelihood of an event with the measure varying between 0 and 1. But in any case, when you express your degree of belief, even if you express it based on your expert knowledge, you must respect these axioms. Like, if you say, again with politics, the probability of Monti being the next prime minister is 80%, and what is the probability of Monti not being the next prime minister? You can say 50%. It's inconsistent. If you say 80% of being the prime minister, you should say 20% of not being the prime minister. Okay? This means respecting these axioms. So, again, any measure that respects these axioms can be taken as probability. So you can understand that there might be measures of probability which are not consistent, not reliable. Because, of course, I may be wrong when I say Monti can be the prime minister with 80% and not to be with 20%. This satisfies the axioms, but another person could be absolutely not. I don't agree. So, not necessarily the estimate is good, but any measure that satisfies these axioms can be taken as probability. Now, let me define the random variable, which is very important because we deal with numbers. So far, I also spoke about experiments, because indeed, statistics, probability, they describe the outcome from an experiment. They describe floods, droughts. In order to make analytically tractable these events, we need to make an association between the outcome of the experiment and the real numbers. This is the random variable. And in the case of river flows, the association is the measurement of the discharge. So I go to measure the discharge, the river discharge, and I get a random variable. I made an association between an event, the river discharge, or the flood, and the real numbers. Okay. I think we can skip this one. And not just the first sentence is important because it's a way of computing probability in a way that satisfies the axioms, and the frequentists define an experiment and estimate the probability of each outcome by computing its frequency in the long run. Like I did for the floods of the Po River. I have 100 years of data, I have 3 occurrences of river flows greater than 12,000 cubic meters per second, and then I conclude that the frequency of occurrence is 3 over 100 years. This is the frequentist way of computing probability. And this is rigorous because it's based on the computation of the frequency of occurrence. And if you do so, you respect the previous axioms. It's between 0 and 1, the impossible event has probability 0, the certain event has probability 1, and if you consider 2 events and want to compute the probability of one of the 2 occurring, you just have to sum the individual probabilities of them occurring. So this is okay, even if you understand, for the case of the Po River, 3 floods in 100 years, but 2 of them occurred in 10 years, in 6 years. One was in 1951, one was in 1994, and one in 2000. So you say the frequency is 3 over 100 years. One may say, I would say 2 over 10 years, which is very, or 2 over 6 years, which is very much different. So you understand that even if this computation is objective, you understand that there might be uncertainty, and you need very long runs in order to eliminate this uncertainty. But indeed, this is an objective way. If you can define an experiment and you can repeat it, this is an objective way of computing probability. Of course, you can't do it for Monty because you can't repeat the experiment. Okay, now the problem is that what we have to do in probability, when we want to estimate, for instance, the peak river flow, is to be able to assign to each value of the river flow its probability. And this is done through the probability distribution. Probability distribution is an analytical relationship that allows you to associate to any value of the random variable x, which is defined, its probability. And please look at the symbology. We define the random variable with the capital letter, and the outcome is defined with lowercase. And the difference between the outcome is the outcome from an individual experiment. Like the outcome of the maximum flood in 2011. The random variable includes all the outcomes. So the capital X indicates a cluster of variables, a group of variables, a group of outcomes, which we individually indicate with the lowercase. This is the usual symbology that is used in probability. So, what we want to do is to associate to each lowercase x the probability. And of course, the analytical function that associates to x its probability can have different shapes. And therefore, we have different probability distributions. You remember about the Gaussian distribution, the log normal, the Gamble distribution that is used to fit the extremes, and there is the beta distribution, the kappa distribution, a lot of them. And this is understandable because if you consider different processes, it's different the way in which you must associate to each outcome its probability. The example is, the most relevant example is the Gaussian probability distribution, which is also called normal distribution. The Gaussian distribution is not very much useful in hydrology because hydrological variables are typically non-Gaussian. But the Gaussian distribution has a striking property, which is in a way also amazing. Let's say again what I just mentioned. Hydrology is not Gaussian. It means that if you consider the daily river flows of the Po River and want to associate to each outcome its probability, you can try to use this distribution. But when you compare the response of this Gaussian distribution with a frequency analysis, you find that it doesn't work. It means that the distribution is not good. As I said, you can compute the probability of an event by computing the frequency of occurrence. But you can also compute the probability of an event by using the probability distribution. What's the advantage? The advantage is that once that you have the probability distribution, it's an analytical function, it's very much easier to compute probability. But of course, you understand that if you compare the two methods, you should get similar results, equal results. If I compute the frequency of the river flow of the Po River exceeding 10,000 cubic meters per second, and I make this computation on the observed record, and then I take the Gaussian distribution and I do the same computation, I should get similar results. Instead, I don't get them. I don't get similar results. It means that the Gaussian distribution is not good. But if I go to analyzing the monthly values, I would find that the Gaussian distribution is not so bad. If I go to annual values, mean annual river flow, I would find that they are almost Gaussian. If I go to 10 years of aggregation level, I finally would find that they are Gaussian. This is the striking property of the Gaussian distribution. Any random variable that is averaged over increasing time spans gets Gaussian. Any random variable that is averaged, random variable expressed depending on time in this case, I forgot to make this clear. If you have a random variable like river discharge that is expressed depending on time, if you average over increasing times, 1 week, 10 days, 1 month, 1 year, 10 years, you get to Gaussian data. Maybe that you need to average longer for some variables or on shorter period for other, but at the end you get the Gaussian distribution. And this is striking. This is what the central limit theorem says, but it's really striking. If you think about any possible random variable, you average over increasing times, the random variable should be continuous in time. You get data that are Gaussian. So you have an analytical function that is capable of describing the frequency of occurrence of any random variable, provided that you are average over long times. This is a bit amazing. It means that in a randomness there is an order. And this is the order that we want to understand. This is something that, you know, is striking. In randomness there is an order. Okay. There is one final slide. When the random variable can be discrete or continuous. So we have probability distribution for continuous variable and probability distribution for discrete variables. In our case, we always talk about, not always, but 99%, we talk about random variables that are expressed depending on time. Still, they can be discrete or continuous. For instance, the annual maxima is discrete, while the river flow is a continuous random variable. And you have different probability distribution to describe discrete or continuous variable. The Gaussian is a continuous probability distribution. And therefore, when you have discrete random variables, the meaning of probability distribution is very clear. Because, like tossing a coin, you get the frequency of getting a net, and this is the probability. The frequency of getting a cross, and this is another probability. very clear. Instead, for continuous variable, there is the problem that you have to distinguish between probability density and cumulative probability. And this is a bit of a complication because, you know, for continuous variable, what is the problem? I try to explain to you. The problem is that the outcomes are infinite. You have infinite possible outcomes because they are continuous variable. And therefore, if you compute probability as the frequency of occurrence, it tends to 0 because any outcome is a single outcome which is not repeatable because, you know, it's a real number. It's impossible to get a replication of a real number. It has infinite digits. So you have this problem. In defining the probability, you have this problem with continuous variable. And therefore, you are forced to define the probability of non-exceedance. Probability of non-exceedance for continuous variable is well understandable, like for river flow. What is the probability of not exceeding 10,000 cubic meters per second? And the probability of not exceedance can be computed according to the frequency definition. You get a record of data. The frequency of occurrence of each single observation is tending to 0, but the frequency of not exceedance, you can compute it very easily. And the frequency of not exceedance is also called cumulative probability. Cumulative. Why cumulative? Because not exceedance means that you are computing the probability of all the lower values. It's an integral, it's a cumulated probability. Any individual contribution is tending to 0. But when you compute the cumulative probability, you integrate this individual contribution and you get a well-defined number. How many times the Po River didn't exceed in the past 100 years 10,000 cubic meters per second? It's very easy to compute. You go there and tuck, 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 you count them and you divide by the total number of observations, you get the frequency of not exceedance. And the individual contribution